Our next speaker is Dr. Emma Bradley, who not only did she come all the way from the UK to join us here today, but she is an expert on beer. So we have lots of reasons to be grateful for her presence. She has her PhD in bioorganic chemistry from the University of Leeds, worked for many years on investigating beer and cider flavor and stability. So I would love that job. And she currently is the head of programs of food quality and safety at the Food and Environmental Research Agency, FERA, which is in the UK and is affiliated with the European Food Safety Authority and the European Union reference laboratories for food contact materials. She's written more than 30 peer-reviewed papers on food contact materials and is going to talk with us not only about the European Union and UK sort of structures and processes for migration testing, but also some examples and issues that she's been involved with.
Okay, thank you. I did research beer, but unfortunately when you tend to be researching beer flavour, you're generally tasting it because there's something wrong with it. So the general response of "ugh" was not one that they really wanted. But no. So yes, that was my first job after university. But when you tell people that you move from researching beer to researching food packaging, general response is unlucky. But, so today, and I hope I'm not going to be too technical in the presentation. I hope I'm going to be able to address some of the questions through this talk that were given to the previous speaker. And I can almost guarantee I'll go on too long, so keep waving that time thing at me. So basically, this presentation will try and cover some of the methods that we use to identify those chemicals, to identify those impurities, those reaction products, those breakdown products, to try and understand what has the potential to migrate into our foodstuffs, and also to give some details on how the concentrations vary with time and temperature. I think whenever giving such a presentation, when I can put up a chromatogram with potentially 200 migrants in, what's really important at the outset is just to say that packaging is beneficial. We've had discussions on this already, but it really is important that we do recognise that we do need packaging. We do need to protect the foodstuffs from spoilage. However, the transfer of any chemicals from packaging does have the potential to have a negative impact on the quality and on the safety. There's no food contact material at all which is completely inert. People often say, well, what about glass? Well, there's metal ions in glass. Those metal ions will transfer into acidic foods. Nothing is completely inert. There's no products that will give zero migration. They just don't exist. And therefore, we need to ensure the safety of these materials. This slide shows the European legislation. So basically, we have the framework regulation, which is the regulation which applies to all food contact material types. That also empowers the European Commission to set specific measures for other material types. And as you can see from this list, then we've done a lot on plastics, but we haven't done a lot else. So what do we do for can coatings? Well, for can coatings, we would have to demonstrate that they would meet with the requirements of the framework regulation. And that has a general requirement that materials shouldn't transfer their constituents at levels could endanger human health or alter the organoleptic properties of the foodstuff. So that's bringing that sensory side in as well. And that is a legislative requirement within Europe. We've talked about the previous speaker spoke about migration testing, and the rules defined to test for compliance of migration are set in our legislation in Europe in the same way as they are by the FDA. What the legislation allows us to do is to perform extraction tests, carry out migration modelling, test into food stimulants and test into foodstuffs. Now, this is the case study example I was saying before in terms of I'll work through. What should also be noted when thinking about this in terms of when a test laboratory takes a sample off a supermarket shelf, that it's not necessarily the case that if it's present in the food, it has come from that packaging material. And we don't want to talk about bisphenol A, but when we are talking about bisphenol A, something that is ubiquitous will be present everywhere. And it's really important that your methodologies address this. You will always detect bisphenol A. It's what your reporting limit is, not what your detection limit. And that's a really important criteria for those components. And also, some migrants will react with food components. So again, if you've got a reactional group in your substance, there is, in your chemical that you're using, there is the potential for it to react with the foodstuffs. So they're things that need to be borne in mind when carrying out the testing. So what can migrate? We call these IAS and NIAS in Europe, and I don't know if you use the same terminology here, but IAS are those intentionally added substances, and NIAS are the non-intentionally added substances. So the IAS are the substances that are the known ingredients that are used to manufacture, in this case, the can coating. You know them, you put them in. But actually, when you manufacture a polymer, a can coating, any other material article, you're generally applying high temperature, you're applying high pressure, and you're removing solvents, baking, etc. So there's plenty. It's not just what goes in that's important. It's intended that it will react. So as a consequence, there'll be known or unknown isomers. You'll know that something's there from the testing your starting materials. During the processing, things can react, produce new potential migrants, and indirect sources such as printing inks, external coatings may contaminate the food contact surface. We did a research project a while ago when we thought here we are, a group of people all trained in chemistry. We can predict what reactions will occur if we make a polymer using these 10 ingredients. So we gave this huge list of 250, 300 potential reaction products. We tested it, and we probably got 10% of the peaks that we found. And what we found that to be was the impurity of the starting substances. And actually, those impurities in that, they're not meant to be incorporated into the polymer backbone, and therefore they were labile and free to move and free to migrate. So that again, that gives you that first step. It's very important to understand the quality of the starting substances that are going in, that they don't give any impurities that could be avoided. So in terms of the analysis that we do, and we can do two types of analysis. If we know what we're looking for, we can develop, validate a specific method using very sensitive technologies. We can direct our chemistry just to look at that substance. And historically, that was what we did. We took the starting substance, we tested its migration, we saw that it was below any level of concern, it was okay, or it wasn't approved. Now, as technologies have improved, we're working more towards screening. So we can now monitor the extracts of packaging materials and, I won't say detect anything that's in there, but detect anything that ionizes in the methods that we're applying, which basically gives a whole new ballpark in terms of the amount of work that's needed. So you just said this, so can coatings, IAS, these are things, and the methods developed and validated in line with levels of interest. And within Europe, it was touched on before that FERA is the national reference laboratory for the UK, and this document, it was generated by the Community Reference Laboratory, that is now called the European Union Reference Laboratory on Food Contact Materials. And certainly a lot of the technical guidelines that we follow, we've developed through that route. So their website would be one for people to look at. So the NIAS uses a whole range of very expensive equipment, very sensitive, very selective. And we've developed protocols to follow. So we've developed these in-house at FERA, and we've used them to support dossiers to the European Food Safety Authority. And there is nothing written in the legislation, but there is an ILSI monograph that was published in July 2015 on guidance on best practices on the risk assessment of these NIAS. But fundamentally, they all follow the same trend. So we basically What I think is very important to highlight is those initial discussions, is the importance of understanding what's in your starting materials. If I was to, so sometimes I will be given a packaging material and say, can you tell me if this is safe? No. You know, we'd never take on work like that. You can't do that. You can never be 100% sure that your methods will detect everything. What you can do is working with the industry to understand the raw materials, the starting substances, analyse those, take it through the process and get the best picture. You will not necessarily understand, and you still won't be able to detect everything. You certainly won't be able to identify everything or measure the concentrations, but you will be using the best practices possible to achieve that. So in terms of the NIAS and using GCMS, so this is just a GCMS trace of a solvent extract of a food contact material. And basically you'll see 4 or 5 peaks you can probably see in there. For GCMS, there are libraries. These libraries have been developed over time. You can analyse your substance, you can ionise it, and you can compare the spectrum obtained with libraries. In some cases, you'll get a match. In some cases, you won't. And then what do you do? And that was the historical state until the high-resolution technologies were developed. And once we've got the high-resolution mass spec, now we can detect those NIAS because we can screen to accurate masses down to 4 decimal places. Once you measure the mass of a substance down to the 4th decimal place, there are only so many ways you can arrange your elements to give you that, taking into account the accurate mass of the elements. You can also look at isotope spacing and intensity, which will tell you whether, for example, you've got a chlorine present or something like that. You can use positive and negative ionization modes to give you greater coverage. So by utilizing these technologies, you've got so much more opportunity to detect those substances that have the potential to migrate. Again, working with industry allows you to develop a database. So if you know everything that's gone in, you can actually, we've developed macros that allow us to predict how things will react. And therefore, we can have a database with 10,000 substances in for a given system. We can search our accurate masses from our analysis against that database and therefore propose identities. That's no way enough. But I'll speed up even more. So we can work that. So again, it's very important to be working with them to actually understand what's needed. Quantification is really challenging. We still are not there. We're only ever given estimates of concentrations. But it's, again, it is applying the state of the art. It's the best that's available at a given time. And one thing we've done recently to actually help us to demonstrate that the techniques we're using in this high-resolution technology are giving good estimates of concentrations is compare functional groups using NMR. So again, it just adds some confidence to the data that we're generating. So extraction, basically then, from that extraction data of the food packaging, we can have our estimated concentrations, we can calculate, assuming 100% transfer, and what the worst case concentration in food is. We can also use migration modelling, which maybe we'll talk about later on, because that helps us to understand that the simulants and the time temperature conditions are correct. We've already talked about the migration into simulants with previous presentation, and it's the same in the EU. Our simulants are slightly different, but we have the same approach. And then just finally, a few slides on factors affecting migration. In a polymer, in a coating, then migration is generally a diffusion and partitioning process. So it's dependent on the nature of the food contact material. It'll be dependent on the type. So in the previous presentations earlier on, we saw there was vinyl, polyester, epoxy. Each of those will have different diffusion characteristics and therefore different rates at which chemicals will move. And this just basically shows for things like plastics, it can move from within the matrix into the foodstuff, and also depending on the food, depends on how far it will move into the food. The nature of the substance, there's different chemistries. I've mentioned before, the potential of the substances to react with the foods exist. Also, substances will be different molecular weights. This is just a migration modelling output where you can see that a 200 Dalton molecular weight additive is smaller, it moves faster, it migrates quicker. And that's fundamentally all that's showing. The interaction between the food and the packaging. With plastics, for example, does the foodstuff swell the polymer? Does it swell the coating? Does it increase the interaction and thereby increase the migration? And also, being diffusion related, it's time and temperature dependent. This is a bit more complicated slide, but really shows the nature of the foodstuff. So looking at the migration of a polar compound, tested, this was not a beer experiment, this was a horrible experiment, mixing pork mince with lard. I don't know if you have lard, but it's in the US, but thankfully one of my colleagues did this. So, yeah, and then doing migration testing. We went up to 4 days. We had to stop then because it was really getting quite unpleasant. So they told me, yeah. But effectively what it's showing is obviously, if it's not soluble in the foodstuff, it will not enter into the foodstuff. There will be a partition between the packaging and the foodstuff, and that's important when you're thinking about what we talked about earlier in terms of your hazard and your risk. Does it actually migrate? And we can also do migration into foods themselves. We use simulants because that allows the industry to then sell it for a number of food types. But what if you only want to sell it for one food type? Then you can do that. And often, if you want to demonstrate that it's if it failed into a food simulant and you wanted to continue with it to a specific use, you could test into the food. When you do that testing, you would do it under the worst foreseeable conditions of use, so that's those accelerated time and temperature conditions. And one of the things in terms of, this is more related to when we're testing for compliance purposes. If you've got a solid food, you can test the foodstuff at the surface and in the bulk, and that will give you some evidence to demonstrate that it's coming from that packaging material rather than, as for those ubiquitous chemicals, from another source. So there are tools that we use to improve the testing. So in summary, and breathe, it's the ever-advancing analytical instrumentation which has helped us detect what we always say is more and more of less and less. We detect more substances, we can get to much lower levels as the technologies improve. It makes our job obviously more difficult, but it's important to understand everything that has everything that we can detect that has the potential to migrate. Sensitivity is continuing to improve. There's still challenges to identify and quantify everything, and in the EU legislation, we basically say it's the business operator's responsibility to do everything available to them to assess these substances. We could use migration modelling, use the migration into simulants, but for migration into foods, we'll give you the best data for your exposure estimations. And then these are the poor people that do all those horrible experiments I was talking about, and some nice pictures of York, where our facility is in the UK, and just to show that we have nice blue sky days in England as well. We've photoshopped this to make it look that way. So thank you very much.